The grade sheet is up here in case you didn't notice. If there's any discrepancies, if something looks wrong, let me know. Okay. So we're going to do the static equilibrium problems now. This is chapter 12. First one's a conceptual question. Number 7. You have this rod here that's pivoted. There's like a hinge here. And there's a cable here. It's tied to down here and at the ends. And a force is applied at some distance here from the hinge. Okay, and the question is, if you raise the point of application, if you move this upward, the point of application of the force, but you keep the magnitude the same, what happens to the tension in the cable? Okay, you may want to draw, and if you have a hard copy, you may want to draw a vector here and call it T. That would be the tension in the cable. It's exerting a force at this point along its length, like this. So, oh, and I just realized something. This bar or rod here, it can have some mass. It's irrelevant because it's vertical, right? So, in a gravitational field, the effect of the weight is at the center of mass here. It goes right through the pivot point here. So there's no torque due to the mass of the rod. So the mass of the rod is irrelevant here. So what do you think? What's going to happen as you raise the tension, as you raise the point of application of this force, but keep the magnitude constant? What's going to happen to the tension in the cable? Is this intuitively obvious? It's got to go up, right? And the reason is, this is static equilibrium. The torque about any point has to vanish. Otherwise, you would have angular acceleration, and this is static equilibrium. So we naturally choose this point here to be this axis, or this point to be our origin. There's we can think of this as a clockwise torque due to this force. It's being balanced by the torque due to the tension. And if you wanted to, this is a conceptual question, but if you wanted to calculate it, one way to do it is to take this component of the tension times this distance. That would be the torque. But for here, we don't really actually need to worry about that. Due to the tension here, there's a counterclockwise torque, and those two torques have to vanish. And if I double this distance as I've drawn here, keeping the magnitude constant, that's going to double the torque. I have to double the torque due to this tension for this to remain in equilibrium. So it's going to double the tension force. Because the moment arm here is the same. You know, we're not changing the point of application of this tension. So for keeping the magnitude of this force constant, the magnitude of the torque here is proportional to the distance, to this distance right here. If you double it, you got to double the torque. Any questions about that one? Okay, this is also 7, but this is a problem. It's a diver problem, all right? So we have this, this is a diving board. There's a diver here, right at the end. And there are these, you have to have these supports here, right? So they think they call them pedestals. Is that right? I can't remember. Or was that something else? Yeah, they call them pedestals here. So there's a nice picture in the book. Okay, I've just drawn the force torque diagram here. So we're in. I didn't put it on here, but there's of course a well, here it is. It's represented here. This is in a gravitational field, right? There's gravitational field. So we're going to neglect the mass of the board, and we're also neglecting something else here. Anybody ever walk onto a diving board? What do we? Yeah, right. We're neglecting the fact that it's going to flex here, right? Okay. So it's a stiff board of negligible mass. The problem here is to find these pedestals here, or the connection points, are going to exert some forces, have to exert some forces here. Because otherwise this mass will just, it won't be in equilibrium. So, to proceed here we need to draw these forces, and you can probably, with a little bit of thought, you can realize what directions they have to be. The force here, exerted by this pedestal, has to be downward on the board, and the one here is going to be exerting a force upward on the board. But if you don't see that, it doesn't matter. You can just guess. We're going to call this the positive direction of F2, and call this the positive direction of F1. We're free to do that. And if the math gives us a negative value for either one of these, then it points in the opposite direction. We've talked about this before, right? In fact, I think we talked about it recently. Again, we talked about it several times in this course. Okay, so the first condition of equilibrium here is there can't be any net force. Otherwise, the center of mass would be accelerating. So I can see here that the total upward force is F2. The total downward force is F1 plus mg. So I have to have this balance here. And I have to have also the second condition, which is there's no torque. So I'm going to look about the end here. I'm going to take this looks like the most convenient point. There'll be no torque due to F1. This is an unknown, but it's not going to contribute to the torque if I choose my origin here. So I'm going to choose this to be the origin. And now I can see that, I can see now that F2 has to point in the upward direction. Why? My origin is here. I can have no torque. So the torque due to the weight here is this way, right? It's clockwise. The torque here has to be the opposite direction. So F2 has to point upward. And now the torque balance about the origin is this force times the distance has to be this force, mg, times that distance. Okay, so that's one equation and one unknown. We know everything here except F2, so we can find F2 and I get this value, 1740 newtons. And again, it's pretty obvious that it's pointing upward. There's going to be the pedestal here is exerting an upward force. By Newton's third law, the diving board is going to be exerting a downward force on the pedestal. And it's going to cause it to compress. That's one of the questions they throw in here at the end. So this pedestal is going to be compressed. I think it's obvious. And it's clear from here, from the math here, to have equilibrium, the force of the pedestal on the board has to be upward to balance the torque due to that, due to the weight there. Well, once we have F1, once we have F2, now I see that once I have this value, I have one equation and one unknown. I can find F1. And F1, we can calculate it. And again, I think it's physically obvious here that this pedestal is going to be stretched. Okay, this is going to have to be, the board's going to have to be attached to the pedestal. It'll be stretching the pedestal here, because the force of the pedestal on the board is downward. That means by Newton's third law, the force of the diving board on the pedestal will be upward. It's going to cause it to stretch. And we get a value here. Okay, any questions? That's a sort of a simple problem, and maybe not that simple, but it's an elementary problem in equilibrium. Anybody have any questions? Oh, here's this. I mentioned that I actually did with a student an experiment on this. I can't remember what our motivation was. So I have to look at the paper. It's been a while. This was done in the 90s. So here's the idea. You have this wheel here. It's not going to matter. Its moment of inertia is not going to matter. Why? There's no inertia here. This is, I think we talked about this before. This is equilibrium. So we don't have any motion. So all that's important is this is circular here. This is some kind of wheel. Its moment of inertia is irrelevant. A force is applied at the axle here, and we actually did this. And I told you guys before, with a hanging weight here. And now what's interesting here is as you start to increase the magnitude of this force, all right? There's going to, and when there's no force, there's going to be a normal force here. There has to be, because it's going to has to balance the weight of the wheel. But as you exert a force here, this horizontal force, and continue to increase it, slowly increase it, the normal force is going to get less and less. And eventually the normal force is going to go to zero. There's going to be a precise value of applied force here, such that the normal force just goes to zero. And the reason that's interesting is, suppose you're applying that force, and that, in fact, that's the problem here is to find that force, okay, that critical value of the force. If you're applying a force that's the normal force is zero, what happens if there's a slight fluctuation? And there are going to be fluctuations here due to vibrations, just due to temperature. There are fluctuations. There's things in air, right? And this apparatus, even if you put it in a vacuum, this apparatus has temperature, so there's going to be fluctuations. Now, realistically, typically those are going to be dominated by building vibrations, right? This is one reason that if you visit physics departments at universities, you'll find that the labs are usually in the basement. Have you ever noticed? You probably don't know what I'm talking about, but why is that? I'm sorry?
Temperature control.
I never thought of that.
Less vibration.
It's the vibrations. Yeah, that's the main reason. Yeah. Okay, so we're applying just the right force, which we're going to calculate, such that the applied force here, such that the normal force goes to zero. What if there's what if the wheel rotates very slightly in this direction? In this direction. What's going to happen? Well, to see it, what's going to happen to the torque? We can take the torque about anywhere, about here if you like. Let's take the torque about here. What's going to happen to that torque? We're applying a force of constant magnitude and direction, and the wheel rotates just a very small amount. What happens to the torque? Does it go up, does it go down, or does it stay the same? Oh man, what's with you guys today? Is this hitting the end of the quarter here? The torque goes up, okay? Because the moment arm, see this moment arm distance here? If this thing moves a little bit, that distance is going to go up. So what's going to happen? We have a name for a system for this situation. What is it? What kind of situation is this? This is an instability. The slightest fluctuation here going this way will increase the torque, and that's going to make it rotate more, which will cause it to rotate even more because the torque just keeps increasing. This is unstable equilibrium. The situation here, when the normal force is zero, is unstable. It's unstable going that way. Everything's fine going the other way. So it's not like a ball. It's not like a ball on a hill. It's more like a ball. It's like a ball here. Okay. If I look at fluctuations here, it's stable this way, but here, this is just supposed to be the derivative is supposed to vanish here, okay? But the slightest fluctuation here, and it runs away. So that's what's interesting about this system. It's an example of unstable equilibrium. That was probably our motivation. Was probably it. It does have practical applications. When you're moving something along and you hit a step, you want the diameter of this wheel to be substantially greater than the step height here, or you're going to have trouble. Okay, so any questions so far? Let's solve it. So we're going to find this critical value of the applied force. So here's the force-torque diagram. It's kind of busy, okay? You'll notice we've set the normal force equal to 0. We want to find the applied force in the case here where there's no normal force. We've got a weight acting at the center of mass. This edge right here exerts a force on the disk, and it'll have a horizontal component and a vertical component. And you can show, it's easy to show. It doesn't matter. Okay, first let me say this. Here, it's written right here. First let me say this. We don't know what fx and fy are, but we don't care, because we're going to choose this to be our origin. It's going to be our axis here. So they're not going to exert any torques. And all we have to deal with is you're going to see, all we have to deal with is the torque equation. But it's interesting, it can be shown in this situation that the force here is directed directly toward the center. You can actually easily see that if you take another origin. Take this to be your origin. Let's see. Take the center of mass. There we go. Take the center of mass to be the origin. The net torque has to be 0, right? So where does this force point? Where does this F force point? It can't exert no torque, so it has to be directed directly towards there. And that's true whether or not there's a normal force, incidentally. But it's not going to matter, as you'll see. So let's look about the point of rotation. We're going to look about the point of rotation here. You can, to solve this problem, you can look at other, you can try other origins here. And I haven't thought about this for a while. But anyway, let's take, we'll take, it's natural to take this. I'm going to take this one. So I've got to have no torque, right? I see that there are two torques. There's a gravitational torque, gravitational force acting at the center of mass. So I've got to take the gravitational force and multiply by the moment arm here. That distance, I can see here that distance is going to be this distance, which is r, minus h. Minus h. So there's the applied torque about that point. The gravitational torque will be mg times this distance. We'll call that script L. See what I've written right there? We'll call this distance L. And if you look at this right triangle here, you can see that L squared is going to be r squared minus this squared. This we just dealt with. That's r minus h. So we can get a formula for L here. So this takes a little bit of thought. I encourage you to sit down and think about this. This is geometry. This is L in terms of the parameters of our system. So now we have this torque. We just substitute for L here, our expression for L, and solve for the magnitude of the applied force. And we know everything, and we can find it. It's 13.6 newtons. Okay, any questions about that one? Say the next one is 30. Oh, okay, so this is, so we have this, there's this beam here, or bar, that has some mass m, it's uniform. It's attached here, there's a cable. Here we've seen problems like this before, and then there's a mass here at some distance x from this point right here. Okay, here's the quantities that we're given here. All right, now, as you increase x, what's going to happen? The first thing you want to recognize here, this is like the conceptual problem. As you increase x, you move this mass along here. What's going to happen to the tension in the cable? It's got to go up, okay? And if that's, for some of you it's probably intuitive, but don't worry about that. you can see that if we look, let's say about this point, the torques have to be 0 here. So as I move this out here, that's going to increase the torque going this way. The only thing to counteract that is this tension in the cable here. It's got to increase. It's similar to the conceptual question. So the issue here, and this is like an engineering issue, is you want to have, there's going to be a maximum tension in that cable beyond which it'll break. So you want to make sure that it doesn't break. That's the practical problem, when this mass moves all the way out to here, right? So in this problem, we're given that the maximum tension is 500 newtons. We're given all this other information, the weights here, the lengths, and we're going to find the value of x for which you're at the maximum tension. Now, you might say, well, so from an engineering point of view, what do you want the value of x to be? What's the inequality that you...
You want x to be max, right? You want that max distance, so you have the max tension on that.
You don't want the thing to break. Let's all agree on that first, okay? So the maximum tension is going to occur when? Where's this going to be? At the end. So we're going to calculate, in this problem, our perspective is we're going to calculate x such that we have the maximum tension. And we want it to be out here, right? We want x to be greater than L. Now if it bothers you here, just imagine that we attach a massless rod here. You can imagine there's a massless rod here, rigid. And we can move this out here like that, okay? No problem with that, yeah?
Doesn't that change the theta then? If we moved it out beyond L?
Why?
Well, if you moved it out beyond to a length greater than L, theta would decrease.
No, this is fixed. Theta is fixed. We add a massless rigid rod here, and the mass can just, it can move to the side of the cable. Yeah. Okay. So, I just want to point out here, and it's mentioned at the end on the next page here, that x is not necessarily restricted to, and engineers would think x is restricted, but physicists don't. We see, oh, physicists want to think generally here. I can imagine this mass to be over here. I just have to add a little bit. It's not going to affect things. Okay, so here's the force-torque diagram. We got this sort of pivot or hinge here that's going to be in general an x component, a y component. The tension is along the cord or cable here, and we'll resolve it into components. And now the first thing, I want to do the easiest thing here. The first thing is, let's look in the x direction. I see two forces. They have to balance. Or we would have x motion of the acceleration of the center of mass in the x direction, and we don't have this a static problem. So I see that fx has to equal t times the cosine of theta. No question about it. What about the vertical direction? Okay, now I see four forces. The upward force is Fy and t sine theta, and the downward force is little mg plus big mg. All right. And it's natural to take this as like the best origin here because we don't have to worry about fx and fy, which are unknowns. If I take my origin here to have no torque, you can see that there are three torques here. There's going to be, in the clockwise direction, there's going to be mg times x. That's the torque due to this mass here. The weight, which acts at the center of mass, is going to be capital Mg times L over 2. This distance is L over 2. So I add those together to get the clockwise torque. The counterclockwise torque is going to be T sine theta times L. So I get this. So we have three equations, and how many unknowns do we have? Right, because we're specifying t to be at its maximum value, and we're trying to find x. So x is one unknown, and we don't know fx and fy. And one of the interesting things about this problem, this hardly ever happens, but this is unusual, but you'll see that this is one equation in how many unknowns? One. This is one equation in how many unknowns? 1. And what about this? It's just one unknown. So we don't have to do any kind of simultaneous, substitution or whatever. We just solve each equation individually for its individual unknown. So that's straightforward. Fx is going to be t times the cosine of theta. We know all that, so we get a value. Fy is going to be this. I've just moved the t sine theta over here. We can calculate that. And the interesting thing is x. Okay? So when I plug the numbers in, we happen to get 1.5 meters. Well, that clearly was designed. They clearly worked backwards, right? So where's 1.5 meters here? It's actually halfway. So they clearly did that and worked backwards with the numbers. It would be too strange to be a coincidence. But I want to point out that so this is a dangerous situation then, right? This mass, because if you go beyond there, you're beyond the specified maximum tension, so you're asking for trouble. You might get lucky. It may not break, right? On the other hand, if this has been outdoors for a long time, it may break before you get there, right? So it all depends on what they mean when they specify this, what kind of margin of error or whatever engineers call it. But we could have gotten a value. I want to point out that we could have gotten a value greater than 3 meters, and then you'd be okay. Then you can put this anywhere. That's how we would interpret that. Okay, any questions about that one? Okay, so this is like a ladder problem. And it's a ladder problem where we have a frictionless situation here. Now what the authors did here was they want you to imagine there's a little rolling wheel there. They said that, now that I think about it, I think the reason they did that, if you just had an edge there and you said assume no friction, that's just really not practical. Does anybody know why? I mean, it's pretty obvious. I've got this edge, this sharp, this really nice 90 degree. I'm putting up something against it there, and there's going to be a normal force. You think friction's going to be static friction's going to be negligible? What's the pressure there? There can be a huge pressure, right? So typically you can't neglect static frictional forces there. So I think what they're doing here is they're removing that by just saying there's a little roller, like a ball bearing kind of roller here. Once I've got this roller, now it's there will be a normal force. The roller can exert a normal force here, but there'll be no force transverse to the normal force here. Now, by normal here, we mean perpendicular to the surface of the rod. Okay, so the roller here can exert a force, a normal force this way, but it can't exert any force that way because it rolls. It's a roller. So that's what we're going to assume here. So the roller is a way of neglecting any kind of static frictional force up here. But we do have to have static frictional force here. Otherwise, this is gonna slip if this is smooth and there's no friction there. So in fact, in this problem, I think we're going to solve for mu s. I think that's the idea. We're given here's the geometry and the masses, the mass, okay, the weight, and we're given the fact that if theta is less than 70 degrees, this thing slips. Okay, that's what we're given. That's what's specified here. What problem is this? Okay. Yeah, okay. So if theta is less than 70 degrees, this angle right here, so you go this way, you start off here, no problem. Eventually, it's going to slip. So we should be able to find the coefficient of static friction. That's where this frictional force here is going to be maxed out. So we know that if you go beyond 70, We know 70 degrees corresponds to the maximum static frictional force, which will be mu s times the normal force. So here's our situation at this critical point here. Again, it's one of these typical, kind of busy diagrams. I strongly suggest, some of you like to write little tiny diagrams. You don't want to do that here. It's just asking for trouble. There's a lot going on here, right? So you want to make it, I recommend that you kind of make it big. So this is a static equilibrium problem. We maxed out the static frictional force. So again, the x direction is usually the simplest. And this is not an exception. It's just two forces in the x direction. There's the static frictional force pointing this way. Then there's the normal force here will have an x component in the opposite direction. That x component is going to be the magnitude into times the sine of the angle. So this is the balance of x forces. Y forces, I got looks like three forces in the y direction here. N1, the surface here exerts an upward normal force. There's going to N2 times the cosine of zeta will be the upward force here. And the sum of those has to balance the weight here, mg. So we get this. And we got to deal with torque here. I'm sure by now you have that feeling, but if you wanted to stop at this point and just see what you've got, how many unknowns do we have here? How many unknowns do we have? Well, we don't know N1, we don't know N2, and we don't know mu s. Two equations, three unknowns. So the math is telling you got to have another equation. Physically, we know we have to specify that there's no torque. You can have no net force on a system, but still have a torque. It's easy to construct simple situations like that. So we got to get that information in here. So let's take this natural origin. I don't have to worry about the torque due to these two forces because there's no moment arm there. And I see, and it's also nice. What's the torque due to N2? See, N2 is perpendicular to the rod here. So the moment arm is just this distance. Now we're going to have to calculate it, but that's just easy trigonometry. I'll call it script L. And you can see here, this is a parameter of the problem. H, we're given H. So you see this right triangle here. By knowing theta, which is 70 degrees, and by knowing H, which is 3.05 meters, I can find the moment arm distance L. So I've got that torque. It has to balance the torque due to the weight here. And the moment arm there is this distance, which is the hypotenuse times the cosine of theta. So here's our balance of no torques about this point. We've got to get this script L, but as you can you can see here that script L is L times the cosine times the sine of theta is equal to H. So that's how we can eliminate L here. And so we got three equations and three unknowns now. Here they are. And right, this is a shorter problem set. Well, we only had one lecture on the chapter, right? So, we got 15 minutes, and this is the last page, right? Does anybody want to make a bet that I can't stretch this out for 15 minutes? Yeah, I can start talking about it, No, I won't do it. I'm just joking. Okay, so we've got our three equations here and three unknowns. And we're after, what we want to find is the coefficient of static friction. So, what can we do here? What do you see? So we know L. Once you look at this equation, oh, look at this. How many unknowns in this equation? It's just N2. Now I know you'd like to save yourself some time and trouble and just solve for mu s, but you can't do it here. it appears in this equation. There's two other unknowns in that equation, so forget that. So this is the equation to look to because there's just one unknown. So we can find N2 here, because that's the single unknown here. Everything else is known. We can then substitute the value in here and get N1, and then substitute that value in there. We've got to do the whole thing here. This is the easiest way to do it. But I don't think there's any shorter way. So that third equation, the torque equation, is going to give us N2. We solve for N2. Here's the expression. It's kind of weird here, a product of sine and cosine of theta. But that's what we get, because that L is proportional to 1 over sine theta. So this is, we know everything on the right-hand side here. We can calculate it, and I get 143 newtons. Then we substitute it into this equation, the y equation here. Once we know N2, substitute it into here, we can get N1. And I get 396 newtons. And then finally we can substitute something's bothering me here. Oh, there it is. I didn't see it. Okay. So we've now got N1 and N2. Now we can bring those together and put it into the first equation. That's going to tell us what mu s is. So we're using our two values here. I just didn't see that. So we get about a third. You know, it's typical value of coefficient of static friction, roughly. Now I have a note here. This is, you know, this is not a joke. It's, you can look at what for this problem, you have the instructor's solutions manual for this, right?
Yes.
So I invite you to do it. I haven't done it for a while, at least a year. I got a feeling it's been longer than that. But apparently they went to some circuitous route to solve this problem. This is, you know, a professional. It's sometimes not the authors who do the solutions manuals for books like this. There's so many problems. It's sometimes they get somebody else to do the solution. So it's probably mentioned, you know, the person who did it or the people who did it. But all I remember is it was just like crazy. So check it out. That tells you something, doesn't it? I mean, what does it tell you? So here I go. You know, well, we only got. So what do you think? What's going on there? Is this that hard of a problem? Well, it's not simple, right? It's not simple, and you want to step back from it. You know, you always should do this, no matter what kind of problem you're confronted with, physics or otherwise. You don't want to have these blinders on and just, you know. But if you just step back and look at this and realize what you have to, you know, you want to choose the origin here, and maybe well, I don't know. Like I said, I think it's been years since I looked at that. But check it out and see. I just remember being really impressed how difficult they made this problem. They made it much more difficult than what you've seen here. I don't understand that. Okay, any questions or comments? Okay, so the grade sheet's up here. Make sure you just look at your own scores. So this is, and I've got the current running. It seems like there's nobody asked me any questions about it. So I guess it's okay. But if you have questions, if it's confusing to you in any way, ask me. Make sure I've checked off your homework. If you've submitted a homework and I don't have it checked off, that can happen, right? So let me know.